Okay, so let's make sure that we're using our formal notation to write sensible claims. Let's imagine that we're starting out with some objects. A, B, C, and D are primitive objects. They're not sets. Let's let A, B, and maybe C or D if we need them be sets of primitive objects. P and Q are logical predicates, and R and S are binary relations. And what we need to make sure of is that when we write expressions that use operators, that the arguments to the operators are of the correct types. So let's read this one. AD is an ordered pair, and it's an element of A cross B and C.
That is nonsense.
Right. Why is it nonsense? AD is an ordered pair. It can be an element of some set cross another set. That's fine. Here we have a set A cross. Well, now let's look at the second argument. Let's say B and C are sets, but we've ANDed them together. AND is a logical operator. It doesn't apply to sets. Let's try to figure out what somebody might have been trying to say. Suppose that we have these sets. Maybe what someone's trying to say here is that the pair AD is an element of A cross some set that requires that you be in both B and C. See the and there. And note that that would actually be true. A is in A, and D is in fact in both B and C. So maybe that was the claim that we intended. Well, how could we say that?
That makes sense.
Right. Now we've said it correctly. This pair is an element of A cross an actual set that we form by intersecting B and C. All right? So we can intersect sets, we can't AND them. Let's look at another example. Now we've got R implies R or S.
That is nonsense.
Why is it nonsense? It's nonsense because this is a logical operator, or, and that means that it gets applied to logical expressions. What are R and S? Oops, R and S are binary relations. And that bites us here because we have implies also a logical operator, and oops, we have a relation here. What might someone be trying to say when they wrote this nonsense? Well, maybe what they're trying to say is that if an element is in R, then it must also be in R or S. Let's write that the way it makes sense.
That makes sense.
Why? Because now what we have is that, remember, relations are sets. So our union S is the collection of all pairs that are in at least one of them. And now we're asserting that R is in fact a subset of that. So every element must be in at least one of these. And of course that's true because it must be in R. So this is sensible and true. So we're trying to find out what somebody might have meant when they wrote nonsense. But you shouldn't expect the people who read what you write to go through this exercise. You should write what you mean. All right, let's consider another example. Remember that we are allowing this notation for relations. This means that the pair AB is related, A is related to B via R. So we have the claim that A is related to B via R, and we've unioned that with the claim that A is related to B via S.
That is nonsense.
Yeah. Why? Okay. This is a logical claim that A is related to B via R. And this is a logical claim that A is related to B via S. And now what have we done with the two of them? Oops. We've applied the set operator union. What might somebody have been trying to say? Perhaps they were trying to say that A and B are related by at least one of R and S. Okay?
That makes sense.
Yeah. A and B are related by R, or they're related by S. And of course, that means they could be both because this is inclusive or. So this is what we should have written. All right, let's look at this one. Now we're going to define a set, and we're going to say it's the set of all AB pairs such that there exists some third element C, that's in A, such that what? AC and BC are in R.
That is nonsense.
Yeah. Why? All right. AC is an ordered pair. BC is an ordered pair. And is a logical operation. Can we and things that are not logical claims? All right, so what might somebody have been trying to say? Let's look at it, see if we can figure it out. Maybe what we're trying to say is that we want the set of all AB pairs so that there exists a C that's in A such that both AC and BC are in R. Now we have to make the logical claim that AC is in R and BC is in R.
That makes sense.
Sure. Now what we've done is to say what we meant. An AB pair is in this set, just in case there exists a C that's in A, and AC is in R, and BC is also in R. Now we are anding logical claims. All right, so the moral is, be careful, use the notation correctly, and don't write nonsense.